In this video, we are looking at the three great theorems of vector calculus. That would be Green's, Stokes, and Gauss. Also, I sometimes refer to those as the big three. In this video, we are going to look at Gauss's theorem, also known as the divergence theorem for surfaces. And just a quick kind of introduction is that Gauss's theorem states the flux of a vector field out of a closed surface equals the integral of the divergence of that vector field of the volume enclosed by the surface. So one of the first things we need to talk about is orientation. So closed surfaces can be oriented in two ways. The positive orientation is the outward orientation, where the normal points outward into space. So if you have a box or a ball, the outward orientation is outside the box or out of the ball. The inwards or negative orientation points inward toward the surface. The second idea we have is flux, and that's this surface integral of f, a vector field over a surface. And we think of f, if we think of f as a velocity field of a fluid, then the flux indicates the amount of fluid leaving or entering the region bounded by s per unit time. Gauss's theorem says if we let omega be a region in space in R3, so it's some sort of volume, let delta omega, this here is going to be the boundary of omega, be an oriented closed surface that bounds omega. So if omega is, say, something like a soap bubble, both the interior and the surface of the soap bubble, then the boundary will be just the soapy film that makes this up the soap bubble. Then let f be a smooth vector field defined on omega. Then what Gauss's theorem says is the divergence of that vector field over the volume is equal to the vector field integrated over the surface. And we will be doing several examples, and we'll be doing it both ways, both using this volume side, the divergence over the volume, and then also doing this second side, the vector field over the surface side, and verifying that they are equal. Our first example has the vector field f equal to xy squared y, and y, where s is the surface of the cylinder, x squared plus y equals 1. That's a cylinder of radius 1, bound by the planes z equals 1 and z equals negative 1, and including the portions x squared plus y squared is less than 1 when z is negative 1 and equal to 1. So here is our cylinder. This bottom surface is at z equals negative 1, and here it includes the entire bottom circle. And the top over here, this top surface, including the interior of the circle, is at z equals 1, and then the rest of this cylinder has radius 1. So to verify Gauss's theorem, we'll have to do this calculation on the left, that is the divergence over the volume calculation, and then we'll have to compare that with this calculation on the right, the vector field integrated over the surface. So here on this top part, I did the divergence over the volume, so this left-hand side. On the bottom, I do the surface integral of f. This is the right-hand side. So on the left-hand side, first we need to take the divergence of f. So here is our f. Divergence is d dx, d dy, d dz dotted with f, which is xy squared y, y. Derivative with respect to x is equal to y squared, plus derivative with respect to y is x squared, plus the derivative with respect to z is equal to 0. So we have x squared plus y squared is our divergence. And next, for our volume integral, since we're integrating over a cylinder, I chose to convert to cylindrical coordinates. So cylindrical coordinates are the x will equal to r cosine theta, y will equal to r sine theta, and z is just equal to z. Plugging now into our triple integral, because we're integrating a volume, so dz is going from negative 1 to 1. That's the bottom of the cylinder to the top. dr goes from 0 to 1. And then our theta goes from 0 to 2 pi. And then I need my divergence, which is x squared plus y squared, converted to polar coordinates will be, my x squared will be r squared cosine squared theta, my y squared is r squared sine squared theta, and then I also have to multiply by my Jacobian, which is equal to r for cylindrical coordinates. When I do this integral, I get pi as my final answer. As I had mentioned, to verify Gauss's theorem, we now have to do the same calculation using the surface integral. So I wrote down here that we're doing the surface integral, and I borrowed the surface integral formula from our video on surface integrals. So you'll do the double integral of f composed of phi, where phi is your mapping from your domain to your surface, and then the normal to your surface, which is tu cross tv. If you recall from our video about parameterizing surfaces, to get the surface of a cylinder, we broke it up into 3 different surfaces. First is this band around kind of the main body of the cylinder, which is S1. Then we have this top disk on top, the circle on top, along with the interior of the circle, is our S2. And then the circle on the bottom, the disk, which is the circle in the interior of the circle, is our bottom surface, which is S3. I start by parameterizing S1, the band around. So phi, our parameterization, goes from theta and z to 1 cosine theta, 1 sine theta, and z. And you notice that 1 is set at, our radius is set at 1. We don't want the interior of the cylinder, which is why the radius doesn't go from 0 to 1. It's just fixed at 1. So this will give us our circle, our 1 cosine theta, 1 sine theta, and z will give us the height, will give us the circle going all the way up to the cylinder. This is our parameterization of the surface of the cylinder. Then we can do f composed of our phi. So f of this theta and z will be f of cosine theta, sine theta, and z, and then plugging in cosine, sine, and z into f. Well, first I need to find f. Here's our f. It's xy squared, so that will be cosine sine squared. Then f up here in our problem statement. The second coordinate will be x squared y. So down here in our f composed of phi will be x squared y. That'll be cosine squared sine theta. And then finally, and the last coordinate will be y, so that will be sine theta. Next we can take this, now this is f composed of phi. Now we can take our partial derivatives of phi with respect to theta and z. So partial derivative with respect to theta is equal to minus sine theta, cosine theta, and 0. With respect to z, here it's 0, 0, and 1. And now I can plug into my formula. So I have my double integral. So I'm integrating, well here my theta was parameterized by u and v, but in this example we're parameterizing by theta and z. So theta is going to be between 0 and 2 pi, and z is going to go between -1 and 1. And then I have my f composed of phi, which is cosine sine squared sine, and then sine theta, dotted with my norm, tu cross tv, which is equal to cosine theta, sine theta, and 0. And when I do this integration, I'll note that it is equal to pi. Looking now at S2, this top surface shaded in yellow, my parameterization of this disk now is phi r theta equals r cosine theta, r sine theta 1. So z is at the height of 1, and r cosine theta, r sine theta gives us this entire circle of radius r, as well as the interior by letting r go now between 0 and 1. At this point, we do want the interior of the circle because we want the whole top. Now my f composed of phi is now f composed of my r cosine theta, r sine theta. Again, looking at our problem statement to get f, we get xy squared. So that's r cosine theta times r squared sine squared theta. So we get r cubed cosine sine squared theta. And then our y term is going to be x squared y. So that's going to be our r cubed, our cosine squared sine theta, and then our final, looking at f in our problem statement, our final coordinate will be y, which is just equal to, let's see, where are we? Then phi of 1 will be r sine theta. I can do the cross product, and to save space, I just have 0, 0, r, and then I can plug into my equation when so it's a double integral, theta going between 0 and 2 pi, r going between 0 and r of r. When we do this dot product, this gives us 0, the second term gives us 0, and then we have an r times r sine theta, so we have r squared sine theta. We do the integration and we get 0. Similarly, S3 will give us 0. So for this whole surface integral, f over the surface, we get pi from S1, 0 from S2, 0 from S3, so our final answer is pi, which agrees with what we did using this divergence over the volume. So again, the second calculation we did was the surface integral of f, so integrating f over the surface. And these two calculations are equal, which is exactly what we would expect given Gauss's theorem. I do often refer to this summary sheet of path and surface integral. I have a full video just going over this one sheet. Often when I refer to it, I have it in a little corner somewhere, so you might want to screenshot this so you have access to a full size copy. And the idea behind this sheet is it organizes all the different path and surface integrals. So this top line talks about, or top row talks about path and integrals, whereas the bottom row talks about surface integrals. Here we're talking about scalar functions. So this is path integrals of scalar functions. This is surface integrals of scalar functions here. Over here, we have vector fields. So this is path integrals of vector fields, surface integrals of vector fields. And then I have small notes on Green's theorem, Stokes, and Gauss. Oh, and one other note I should tell you. I originally made these videos for my daughter who was in college at the time, and I couldn't remember what the name of this Greek letter was, which is phi. And so we just called it, because it looked like the green lantern symbol, we just called it the lantern function. So I did update my video, but every now and then I might still call it lantern just out of habit, so you'll know what I'm talking about, but also a warning, no one else calls it that, so just be warned. So to start, I'll just mention that Gauss's theorem states that the flux of a vector field out of a closed surface equals the integral of the divergence of that vector field over a volume. The results parallel Stokes and Green's theorem in that it relates an integral over a closed geometric object, curve or surface, to an integral over a contained region, surface or volume. Another concept we should talk about is orientation. So if you have a closed surface, so think of like something like a ball or a can, but it's definitely closed, or a box, it's closed. So the negative orientation is things going in towards your surface, so going into the ball or into the box or into the can. The positive orientation is pointing out of the surface, so out into space, so out of the ball, out of the box, out of the can. That's the positive orientation. And orientation is important since these surface integrals often are physically interpreted as flux. And if you think of F as a velocity field of a fluid, the flux indicates the amount of fluid leaving the region bound by S per unit time. In other words, it's the amount of fluid leaving through the surface. So an inward orientation means that fluid is entering, whereas a positive orientation will mean fluid is leaving the surface. Here is Gauss's theorem as a formula. First, we have a volume, omega, and an example of a volume might be a soap bubble, and the volume includes the interior. So it's a region in space in R3. Then our boundary, which we designate with delta omega, is an oriented closed surface that bounds our volume. So in the soap bubble example, our soap bubble with the interior is the volume, and the boundary would be just the soapy film on the outside. So if F is a smooth vector field defined on our volume, then, according to Gauss, we would expect the divergence over the volume will be equal to the surface integral of f over the surface. We will do some examples, so hopefully this will become more clear. Our first example has our vector field f is equal to xy squared y, and y. And the surface is the surface of the cylinder of radius 1, x squared plus y squared equals 1, bounded by the plane z equals 1 and z equals negative 1, and including the portions x squared plus y squared less than or equal to 1 when z is between negative 1 and z. We want to verify Gauss's theorems. To verify Gauss's theorem, we're going to have to calculate flux both ways, first using the volume integral and then using the surface integral. So here we'll start with the volume integral. With the volume integral for my Gauss formula, I see I will need to calculate the divergence of f. So here I have del dot f, del is d dx, d dy, d dz, and my f, which is given here. So I have my x, y squared, my x squared y, and my y. Partial derivative of this with respect to x is y squared. Partial derivative of this with respect to y is going to be x squared. And the partial derivative of this with respect to z is 0. So we add them up and we get x squared plus y squared. Looking at my formula, I see that this is a volume integral, meaning we will have to do a triple integral. And since we're integrating over a cylinder, we are going to use cylindrical coordinates. Here I have my parameterization for cylindrical coordinates. My x-coordinate will be equal to r cosine theta, y will be equal to r sine theta, and my z-coordinate is just equal to z. Since my vector field and everything else was given to me in rectangular coordinates, to move to cylindrical coordinates, we will need to calculate the Jacobian. For now, I'm just going to tell you the cylindrical coordinate Jacobian is equal to r. I'm just about ready to set up my triple integral, except that I need to convert my divergence from rectangular coordinates into cylindrical coordinates. So I have my y squared, which is r squared sine squared. I don't know why I rearranged these terms. And then I have my x squared, which is r cosine squared. And then I have my r here is my Jacobian. Once I have my integrals set up, then I can integrate, plug in, and my answer will be pi. Since we want to verify Gauss's theorem, I need to do this calculation again using this other side of the equation, the surface integral. So I summarized my calculations that we just did for the volume integral, and I reminded myself that this calculation was divergence of f over the volume, and it was a triple integral. To remind us where we are on our summary sheet, so we're doing Gauss's theorem. We just calculated this triple integral, the volume integral, and now we're going to verify by calculating the surface integral. And note that this is a surface integral of a vector field, and this is how we calculate surface integrals of vector fields. So what I've done is I've put my formula for surface integrals of vector fields over here so that we can refer to it. To do the surface integral of this cylinder, we're going to break the cylinder into three distinct surfaces. The first one is S1, which is the band or the wall of the can, the cylinder. S2 is the top surface, and S3 is the bottom surface of the cylinder. If you watched my video on parameterized surfaces, you may recognize this is the exact parameterization we did as one of our examples. So we are going to start with the surface S1, which is sort of the body of the can out here. And the thing to note about this is that the radius is going to be fixed at r equals 1, because if we let r go from between 0 and 1, then we're including some of the interior of the can, part of the volume of the can. But we don't want the volume, we only want the outside surface. So think of if you have a soup can and you empty it out and all that's left is the metal on the outside. That's what we want. So here I have my parameterization of my cylinder. So I have 1 cosine theta, and I wrote the 1 in just to remind ourselves that r is fixed, 1 sine theta, and then z. And theta goes between 0 and 2 pi, z goes between -1 and 1. Once I have my parameterization, I can do my f composed of my parameterization. So f composed of cosine theta, sine theta, and z. So I need to find my f, which is over here. So it's xy squared. So my x and y squared, so I have cosine theta and sine squared theta. Then I have x squared y, so that will be cosine theta squared, and y would be sine theta, and then y is at the end. Next, I can calculate my normal vector. So I take my tangent vector with respect to theta and my tangent vector with respect to z, because these are my two variables in my lantern function. So derivative with respect to theta of my lantern function is negative sine theta, cosine theta, and with respect to theta, this is 0. Derivative with respect to z, well, this is 0, and this is 0, and this is 1. And then I take the normal is the cross product of t theta, tz. So I have t theta here, tz here. I take the cross product, and then I I calculated the magnitude of this, which was just equal to 1. Now I'm ready to set up my integration according to this formula here on top. And I'm taking this with respect to my two variables of phi, which is theta and z. So theta goes between 0 and 2 pi, and z goes between -1 and 1. And then I need my f composed of phi, which I have written down. F composed of phi here would be my cosine sine squared theta, my cosine squared sine theta, and my sine theta. And then I dot that with tu cross tz, which I have here, cosine theta, sine theta, and 0. And then I can integrate, plug in, and I get my final answer as pi. And one note, I did use a half angle formula to do my integration. I moved some things further up so that I had room to do S2. So S2, I colored in the area that we're doing here. This is the yellow and the red area. And I need to parameterize it. And in this case, I parameterized it as the circle, r cosine theta, r sine theta, where, and 1, because my height of z is equal to 1, where theta goes between 0 and 2 pi, r goes between 0 and 1, and now we do actually want the interior, because here you can see we want the entire disk, including the yellow part, not just the red part. So in this case, we want r to go from 0 to 1, and z, as I said, is fixed. It's at the plane z equals 1. Once I have my parameterization, I can find f composed of my lantern function. So that will be f x y squared. So I have x, r cosine theta, times y squared, which is r sine theta, but that one's now going to be squared. I have my x squared y, so x squared is going to be r squared cosine squared theta, but I also have this r here, so I have an r cubed times sine theta for my y, and then I have my y at the end. Next, I can calculate my t of theta cross tr. That would be equal to my normal. And in the interest of saving time and space, I went ahead and did that calculation, and we get 0, 0, r. Now to set up my integral, my theta goes between 0 and pi, my r goes between 0 and 1, and then I dot my normal with my f composed of phi. So this 0 times the x-coordinate gives me 0, plus 0, this other 0 in my normal, times my y-coordinate gives me 0, and then I have r times r sine of theta. So my integral will be r squared sine of theta, and when you integrate, the final answer will be equal to 0. Similarly, S3 follows a very similar pattern. It'll also be equal to 0. So for this surface integral over the entire cylinder, the top surface and the bottom surface contribute 0, and the band on the middle section will contribute pi. So my entire surface integral will be equal to pi. To recap what we did, first we calculated the divergence of F over a volume, the volume of this can. And written, it says divergence of F over the volume, and it is a triple integral we used. The second thing we did is we calculated F over the surface, so the surface of the can. So it's a surface integral of F. And Gauss's theorem and our calculations showed that these two calculations have the same answer. Looking at this physical interpretation, it says the flux of a vector field out of a closed surface. So that's this here. This is also known as flux. So the flux, the flow out of this closed surface, equals the integral of the divergence of that vector field of the volume enclosed by the surface. And that's here. This is the divergence out. So it kind of makes sense, when you have something exiting a volume, you're going to get flux, a change in the flow across some membrane or surface. So this is really the idea of Gauss's theorem. This example really encapsulates everything, but we will do some more examples anyway. For our next example, we have the vector field F equals 2x, y squared, and z squared, and our surface S is the unit sphere s squared plus y squared plus z squared equals 1. We want to use Gauss to evaluate the surface integral. I have Gauss's theorem here. I have the surface integral on one side and the volume integral on the other side. If they wanted me to use this side of the equation, I assume they would have just said evaluate the surface integral. But since they said use Gauss to evaluate the surface integral, I assume they want the volume integral side. We are actually going to calculate this two ways, but in the spirit of this problem, we are going to start with the volume integral. And I moved things up so we would have some space because later we will need it. So our volume integral here, we start with the divergence. So I have my del operator. I'm going to dot it. I should have put a dot in there with my vector field, and I get derivative with respect to x is 2, derivative with respect to y is 2y, plus 2z. We are integrating over a sphere, so for our volume integral, I am going to choose spherical coordinates. Rewriting now my divergence of f in spherical coordinates, I factored out the 2, and then I'm going to have my 1 plus y, which is rho sine theta sine phi, plus z, which is rho cosine phi. And now I'm ready to set up my triple integral. So I have a rho going between 0 and 1, phi going between 0 and pi, theta going between 0 and 2 pi. I have my 2 out here. I have my divergence. And then I have to remember, because all of this here was in rectangular coordinates, I need to multiply by the Jacobian. The Jacobian takes kind of a lot of steps to calculate, at least when I do it. I did do it out completely for you on the next slide, but I am going to mention, personally, I would just memorize this on an exam. I might set it up on an exam and then put the answer here, just because I feel like it's a very error-prone, very long process. And by the way, my most common error is when I was trying to write a theta, I would accidentally write phi, and then nothing would simplify the way it should. The first step is to write this matrix here, and what it is the first row is the gradient of the first variable in our spherical coordinate transformation. The second row is our gradient of our second coordinate of our spherical coordinate transformation, and our last row is the last coordinate, the gradient of our last coordinate in our spherical transformation. Each of these entries in the top row are going to become a coefficient in front of a determinant. I start by writing this first element as a coefficient, and then because it's the first row, I cross out the rest of the first row, and it's the first column, so I cross out the rest of the first column, and I get the matrix that I'm going to multiply, this coefficient, I'm going to multiply by the determinant of the remaining matrix. So I'm going to cross multiply. I'm going to get minus rho squared cosine theta sine phi squared, and then here minus 0. For my next term, again, my coefficient is the next element in my top row. So that's the minus sine theta sine phi, but the Jacobian matrix, or the determinant matrix, alternates signs between terms. So it's multiplied by a negative, and since this is a negative, it becomes positive. And then the determinant that I'm taking is I cross out, because this element is in the first row, I cross out the rest of the first row. It's in the second column, so I cross out the rest of the second row, and I'm taking it with this leftover determinant. So I'm doing the sine theta, and there's a negative, so minus sine theta sine squared phi, and then this cross multiplied minus rho sine theta cosine squared phi. And to my last term, I take the last element of the first row, that's going to be my coefficient, rho cosine theta cosine phi, and then to get the matrix, I'm going to take the determinant of, since this is on the top row, I cross out the top row. Since it's in the third column, I cross out the third column, and I'm left with this matrix. Here I have a 0, and then minus my rho cosine theta cosine phi sine phi. The rest is algebra, which I'll let you follow. I did underline in yellow the two things that I combined, and in green the two things I combined. So now that you know where the Jacobian came from, the rest of this is integration, simplification. I did have to use some half-angle formulas in there, and I get my final answer, which is minus 8 pi over 3. There is an easier way to do this, and we will do that next, except I have to make one comment. This right-hand side of the Gauss equation here is a triple integral. You can see we had a triple integral over a volume. It is not a path integral. It is not a surface integral. It's straight up a triple integral. The other comment I want to make is, according to Gauss's theorem, we can do this as a surface integral. And actually, I was going to do that for you, but the computation was extremely unwieldy. If you thought that other computation was kind of complicated, this one was even more. It's not that it was hard, but it just took a while and I kept making mistakes. So I don't have that here in the interest of time. But I will show you an easier way of doing this, but this does depend on you kind of stepping back and noticing things. So I have my, my divergence again. I calculated over here as 2, and I factored out the 2, 1 plus y plus z. I set up my triple integral again, but before I start computing it, I just want to point out that I'm going to separate this into 3 parts. So the first one where I take the 1, I separate out the y, and I separate out the z. So the first thing I'm going to say is this part, the triple integral of 1, will give you 2 times the volume of the sphere, because just this part of the integral is equal to the volume of the sphere. Next, we'll look at this part of the integral, the y part. So when we set up our triple integral, we have 2, x goes from -1 to 1, y goes from the negative half circle x 1 minus x squared to positive square root of 1 minus x squared, and then the z goes from, and this is the hemisphere, negative 1 minus x squared minus y squared, square root of 1 minus x squared minus y squared. So this is the typical way we set up our triple integrals a long time ago when we did a volume of a sphere, or we did an integral over a sphere. But what you will notice is you will start your integration. You'll integrate with respect to z first, and you'll plug in these 2 boundaries. When you plug in the top number, you square it. You plug in the bottom number, you square it, and you subtract, and you see that these 2 will cancel out, which is equal to 0. Similarly, if you do the term with z, you'll also get 0. So for the whole divergence over the volume, it's just this one term, and it's 2 times the volume of the sphere, so you'll end up with 8 pi over 3, which is the same answer we got doing it the long way. You can see that there was an advantage in staying with rectangular coordinates, and the reason is because you have these odd functions, the 2 odd functions that once you integrate came up with an even function, and when you plugged in symmetric limits of integration, things will start to zero out. You can also see for this even function, when you integrate, well, I didn't actually do it here, the calculation, but when you integrate, you get an odd function. So when you plug in symmetric limits of integration, it doesn't cancel out to 0, and in fact, you just get a multiplication of a factor by 2. Noticing the odd versus even functions is kind of a neat trick, but it was totally reasonable to have switched to spherical coordinates since we are integrating over a sphere. It's good to be able to do it both ways. This next example is to find the flux through a unit cube positioned in this way here, so this back corner is at 0, 0, for f given by x, y, z, x, y, and x squared y, z. So for flux is essentially this surface integral, a vector field over a surface integral. and I wrote down the formula we have from our summary sheet here for reference. And the thing about this cube is to do the flux, we're going to have to break the cube down into 6 surfaces. So each face is a surface of the cube. I am going to start by working with this top surface here that I colored in yellow. So it's at z equals 1, and the normal points straight up. Remember, the positive orientation points outwards into space. It points away from the center of your solid. So the positive orientation on this plane at z equals 1 is going to be at 0, 0, 1. To make my life easier, I'm going to use this side of the equation, which says I can dot f with my unit normal and then take my surface integral. So here's my f is equal to xy squared, 2xz, z squared minus 2y, and I'll dot it with my normal for this surface, and I get z squared minus 2y. And also, because I know z is equal to 1, I can simplify that even further to 1 minus 2y. Now I can set up my integral, but the integral is really easy because it's just over this square. So x goes from 0 to 1 and y goes from 0 to 1. So finally, when you do the integration and plug in the numbers, you'll see that the flux out of the top is equal to 0. The next surface I will consider is the one at x equals to 1. I colored it in here. So again, it's along where the value of x is equal to 1. The vector normal pointing away is in the positive x direction, so it's 1, 0, 0. Now I can dot f with my normal, and I get x squared y. And again, I can further simplify this because on this surface, x is equal to 1, so I just get y. I set up my integration, and again, I'm integrating over a square, so that's very easy to parameterize. And when I do my integration and plug in everything, I see that the flux through this surface at x equals 1 is equal to 1/2. The next surface I will look at is this yellow one here, where y is equal to 0, so it's along the line y equals 0. And this unit normal, to point away from the center of the volume, needs to be in the negative y direction. So the normal is 0, minus 1, 0. From there, I can dot my f with my normal, and I get 2xz. And I could plug in y equals 0 here, except there's no y term. I set up my integral, I integrate, and I get negative 1. The last surface I will do will be this y equals 1 surface, which I shaded in yellow here, and it's where we're on the line y equals 1. The other two surfaces, I leave that for you to do as an exercise. Now the normal here, it's pointing in the positive y direction, so n is equal to 0, 1, 0. I dot with my normal, and I get 2xz. Again, there's no y to plug in. I put it into my integral, and I integrate, and I get 1 as an answer. I leave it to you to try the x equals 0 and z equals 0 surfaces. Your flux will be 0 for x equals 0. It will be 1 for z equals 0. So once you've done all 6 surfaces, you can sum them up, and the answer will be 3/2. Remember, it seems like it would be bigger, but remember, some of the flux is negative, meaning sometimes the flux is going inwards. So the total flux is 3/2. So we've completed this example, except that we can also use Gauss's theorem. So remember, we calculated the flux over the surface, but we can also look at the divergence over the volume. So here, we can compute divergence over the volume. And this should equal to the flux through the surface. I will start by calculating the divergence of f, which I have written here. So derivative of the first term with respect to x is 2xy. Derivative with respect to y is 0, since there's no y terms. And the derivative with respect to z is 2z. And now, again, it's a volume integral. I can just set it up. And for the cube, this is very easy because x goes from 0 to 1, y goes from 0 to 1, and z goes from 0 to 1. So I do the integration, and I get the same answer, 3/2. So kind of just to look at that example here again, first we did the triple integral. We integrated the divergence over the entire volume. So we calculated the divergence, and then we calculated over the entire volume. And what Gauss allows us to do is we can do that, or we can integrate flux over the entire surface. So, and to do the surface, we had to break it up into 6 different surfaces, which sometimes is the case and sometimes it's not. But again, this is Gauss is what allows us to do either of these, and sometimes one is easier than the other. Our next example has the vector field e to the y cosine z, square root of x cubed plus 1, and x squared plus y squared plus 3, where s is the graph of z equals 1 minus x squared minus y squared times e raised to the 1 minus x squared minus y squared. The problem then is to find the flux of f over this surface. Since this is a video about Gauss, you might guess that we're going to use Gauss. But I just want to ask, why not Stokes? Because this is a question you will need to answer on your exams. And the reason is because we are trying to find the surface integral of f. What Stokes gives us is either a surface integral of the curl, which is not what we want. We don't want the surface integral of the curl of f, so this is not what we want. And we don't want a line integral around the boundary. We want the surface integral. So Stokes won't work for us. But let's look at Gauss in comparison. So what we want is right here, the surface integral of f over a surface. And we can convert it, according to Gauss, to a triple integral of the divergence over the volume. So to summarize, because everything about this problem is ugly, right? F has kind of got all kinds of stuff going on, e to the powers and cosines and sines and square roots. And then also even z, this is, you noticed I didn't even try to graph this function for you. So we're hoping, so really we want to avoid calculating this surface integral directly. So what we're hoping is simplification by Gauss or Stokes. What we'd really like is a 0. Either the divergence is 0 or the curl is 0. And then to summarize why we didn't choose Stokes, Stokes is about the line integral on one side of the equation. On the other side, it's about the surface integral, but it's about the curl over the surface integral, which is not what we want at all, which is why we went with Gauss. Whereas Gauss's theorem is a surface integral, and we can use the surface integral to convert to a volume integral. So using Gauss, we're going to compute the divergence, which looks really ugly, but the derivative with respect to x, well, there are no x terms, so it's 0. Derivative with respect to y is also 0. Derivative with respect to z is 0. So that means this integral here is equal to 0, which means our surface integral is also equal to 0. So hopefully on an exam, when you see something hopelessly ugly, you'll be able to determine if you want to use Gauss or if you want to use Stokes. And then hopefully you will get zeros. So there were like 3 or 4 hopefullys, so I don't know what the probability is. But it might be low. Maybe it's high. Who knows? It depends on what kind of teacher you have. Our next example is to find the heat flux across a unit sphere, where F, our vector field, is equal to the gradient of the temperature, and F, the gradient of the temperature, is equal to minus 2x minus 2y minus 2z. In this example, we're going to use the normal or tangent plane form of our formula because it'll make it easier. Here on our summary sheet, we have our tangent form, but I did also copy it here for your reference. I do also want to add, it is easier using the normal form. Often it's easier using the normal form, especially when the norm is easy to see what it is. It's not something you have to calculate. By the time you calculate, you probably have lost any advantage of using the normal form. So some of the obvious normal forms would be the sphere. The normal is the vector pointing outwards, and so that's the x, y, z vector that points outwards at any point. To make it a unit normal, we're going to divide by r, because r is just equal to the square root of x squared plus y squared plus z squared. So in other words, we've normalized it. We made it equal to the length of our vector, our normal vector, equal to 1. The other obvious normal vector is the plane. Like the cube example we did, for each plane, we just use the normal. We use this normal formula. So you've had one example of this already. But this is our second one. And we could have used the normal on our cylinder example. We didn't do that, but we could have. The top and the bottom, since the top and bottom lie in a plane, that's an easy normal to compute. The top, the normal is pointing up in the z direction. The bottom, the normal is pointing down in the z direction. The sides, the part that it rolls around, is radially out, much like the sphere, but now we're in 2 dimensions, so it's xy divided by r if you want to normalize. So just for comparison, I did the calculation using the heat flux. So the flux being the surface integral. I parameterized my sphere using spherical coordinates. And again, because it's a surface, my rho is equal to 1. My radius is equal to 1. I'm only interested in the surface, not the interior. I did my F composed of my mapping. So here is my F. And I did the function composition. I calculated n is equal to t theta cross t phi, and I just went back a few slides when we did the other spherical thing and took it from there because it was such a pain. And then I plugged into my integral, and after many and I did the dot product, right? This is my f of phi, and then my normal. And then after many calculations, I got to minus 8 pi, and it was actually kind of a lot of calculations. But anyway, this negative sign, I just want to mention, that means that the flux, the fluid, is moving inwards towards the circle, the sphere. But now I want to do this using normals. So the normal for the sphere, again, it's the xyz coordinate divided by r. And for the unit sphere, r is equal to 1, so the normal is just x, y, and z. Now that I have the normal, I can compute f dot n, and then I can plug it into my integral. But I also noticed that the x squared plus y squared plus z squared is equal to r squared. And r squared is equal to 1. So it does help to have some of these insights, which, you know, if you're on an exam, maybe you will, maybe you won't. And if you don't, maybe you're stuck doing this. But if you are insightful, you can see that it's equal to 1. And this integral here is just equal to the surface area of the sphere. So you get negative 2 times the surface area of the sphere, which is negative 8 pi. And I just want to remind you here, when you have this 1 in the surface integral, that means your integral is going to equal to the surface area of your surface. If you did a line integral, the 1 would mean that your integral is equal to the length of your path. At this point, I would normally review everything, but we've done so many examples and this video is getting quite long that I'm just going to finish it here. So that's it for this video. Thank you for watching.